bounded?
Is lambda of t
Bounded.
bounded from above?
Yeah.
Yes, if you assume that the input neurons have a refractory period, then there's no way that lambda of t can get bigger than n over d.
How
long term.
different from a normal photon
Yeah.
channel where
Yeah, the long-term fraction of the time that the well, let's say, if you look at it as a sustainable, if you look at sustainable excitation rates, they can't get above n over d. If all the input neurons also have the same refractory period, then I can't get more than n spikes. Yeah, that's what it is. I guess it takes the highest rate I can get out of any one of them is 1 over d, and there are n of them, so I can't get more than n over d. But that is complicated by the fact I mentioned earlier that really in continuous time, once there's n is bigger than or equal to 2, you could have two of them arbitrarily close together. So there's always a little problem in that modeling, but I don't think it's significant. The right way to think about it is that it's bounded above by n over d.
we have this very this model of Poisson communication channel, which is used to model optical communication, where the input is stochastic process bounded by the A from above under some constraint unit, and output is a Poisson process condition. So doubly stochastic for the process. Isn't it a similar problem in that one?
Yeah, I only hear part of this, but you.
I think he's asking if the problem is similar to an optical communications problem where you have a Poisson, some sort of Poisson statistics.
Where we have the input random process and output is doubly stochastic. Poisson with this process. You know that they're talking about.
And you're asking, I think you're asking whether or not there's some similarity between this and studies that people have done. I forget the Russian guy's name at first, and then Weiner wrote some papers about the optical channels with peak possible Poisson channels that you would, where the input would be the intensity of some Poisson process, and then you try to figure out, and it had some upper limit on it, and you wanted to try to figure out how to distribute things between that lower and that upper level in such a way as to maximize mutual information rate between this input process and the thing that came out. And they found out, and usually they found out that they wanted to either have it at 0 or at the full thing all the time, one or the other all the time, which is not what comes out of this at all. But that is what they found out there. But that was a capacity maximizing problem, and that's not what I'm trying to do here. I'm trying to look at what this is in the case, once again, where the thing works in such a way as to send the most energy, the most information per unit of energy, which is somewhat different than this thing that goes, it doesn't lead to this thing going on and off only. It doesn't lead to a bang-bang solution. But, okay. But yeah, I think there is some relationship about that there are similarities there. But it's a little different problem that you're asking. Okay. So choose time random. We wait to some random length of time t at which it's the next spike is going to come out, and the fixed value that it assumes during that time is a random variable, but then it holds that value. I'm assuming the value lambda gets chosen according to this thing that I'm looking for, f sub lambda of lambda, and then it holds until the next spike. Okay. Now, here's the big assumption in some sense. Assume that there is a known positive integer m such that the neuron's next efferent spike will be generated at the random instant t at which the mth efferent spike arrives. Okay, that is that the instant at which b of t first jumps to the level m, that's when it'll spike. Now, as I say here immediately, I say that ab initio, this looks like an assumption which is naive and dubious. But I think it's right, or very nearly right. Okay. And part of why I think it's right is that if something like this is true, you can adjust that curve to achieve anything that you want, including that I'm always going to count to m before I spike. That's one way you could drop the threshold that would make that happen. If that were your goal, you could do it. Okay? And you could do that by some combination of things leaking off this off the membrane if you wanted. You can make all that happen. I'm not saying it does happen. I just want to look. I think that it's not as unreasonable as it looks at first. And there's that kind of biological thing that says it could be being done. If that's what if the neuron wanted to adjust a thing like that, it could do it. I'm not saying it does do it, but it's capable of it. It has the shape, the biological structure that it can do this if it chooses to do this. And mathematically, it's very beautiful if you do that. Plus, what comes out from that assumption at the end is something really great also that's not built in any obvious way. Okay, so what I'm assuming, therefore, is that I'm going to count to m and then fire. And while I count, that lambda is fixed. And that, of course, means that if I really have a Poisson process of intensity lambda, that I get a gamma distribution with parameter m and lambda to determine how long it is until the m spike comes out. So that's what this is. F of t given lambda is n lambda to the m, t to the m minus 1, e to the minus n lambda t. Because n lambda is the total intensity of lambda here is average per input line, and n lambda is the total intensity of how they're coming along. So I get that gamma distribution with a unit step function on it, of course. And it follows from this that t is absolutely continuous random variable, and that the probability density for t is the integral with respect to capital F sub lambda, Stieltjes integral in general, of f of lambda, which I think is the thing I'm trying to find, times the conditional distribution for t given lambda. So you put that in there, you stuff this guy into here, and therefore you integrate from 0 to t only, and you still have df of lambda there. You're trying to find out what the f of lambda distribution looks like. Okay. Okay. So in this equation, f sub lambda is the probability that lambda is less than or equal to little lambda. It's that cumulative probability distribution it was seeking. And we have used if this thing can now be looked at as a Laplace-Stieltjes integral notation in the following way. Laplace, I guess it's Stieltjes integral, but once I put this into it, and I see that there's a lambda in here, there's nt lambda, if you will. What's happening here is that a Laplace-Stieltjes transform is being taken of something here with respect to this distribution f sub lambda that I don't know that I want to find. Okay? And so, let's see. I mean, put that in there just because it may be that, as you pointed out before, that that thing may not have a continuous distribution. So maybe I better assume that there could be atoms in the distribution of lambda. A lot of capacity achieving things make that happen, but we're not really solving a capacity achieving problem here, and it won't happen to us, but a priori I put in that it conceivably could. Okay, now let's see if I can get it to go to the next page. Yes, it does go to the next page. Okay. So what I do now is I change the variable from t to something that I call s, which is nt. And s is chosen with malice aforethought also, because that's the Laplace transform variable. So now when I do that, I looked at previous equation, and every time that I see a t, I put an s over n in it instead. So I say that the distribution for the time to the next spike evaluated at s over n is the integral with respect to this unknown f of lambda. And now when I look at what happens in there and I replace the t to the m minus 1 by an s over n to the m minus 1, that knocks out a bunch of things. And I get a single n on the top, lambda to the m, s to the m minus 1, e to the minus lambda s over m minus 1 factorial. And here, now you really see it as a Laplace transform because you see this s in there. And we're taking a Laplace transform not from the time domain into some frequency domain. Not that at all. In fact, s is proportional to time. We're taking it from the lambda domain into the s domain, which is a scaled time. It's backwards from the way you usually think of it, but that's what's happening. Okay. So, okay. So now you can just sort of multiply through the terms that don't depend on on lambda on the right side, bring them over to the left, and that's what's happening in the middle there. It's being rewritten that way over here. And, and it follows that if you now look at the inverse Laplace transform operator from this S domain into some domain that I called nu for the moment instead of lambda, because of then the cumulative distribution function would be the integral from 0 to lambda of the integral with respect to nu of this inverse Laplace transformed thing into that domain. It's a little heavy. And if this f sub t was such that the integrand in this above equation, in the above integral over nu contains delta functions in it, then f sub lambda would in fact have atoms in it. It would jump at one or more places. But we do not expect this to be the case in the neuroscientifically meaningful examples, and when there are no such jumps, the probability density for capital associated with capital F would exist, and then it would look like this. It would be lambda to the minus m times the ordinary Laplace inverse transform of what's going on there. Okay. Now I say we show in Appendix 1, but you don't have it yet, but you'll get it in another paper. That we show in Appendix 1 that if a neuron functions in a way that maximizes the rate at which its efferent spike train provides information about its afferent bombardment per joule of energy that the neuron expends, processing its inputs, and generating and propagating its spikes, then f of t has to be exponentially delayed, exponentially distributed with possibly with some delay. In fact, it will have a delay of at least d if it's a, what's the delay that it'll have? D, if it has an absolute refractory period of d. It'll have nothing for a while but the d, and then it'll have an exponential. Nothing else is energy efficient in the long run. Over when the thing runs for a very long time and you go and look at the long-term distribution. That's what it has to be. Okay, so it looks something like beta e to the minus beta t minus d times a step function that starts at d. And I put that into the right-hand side of the equation, left-hand side, excuse me, of this equation over, well, it's inside now. It's inside the inverse Laplace transform operator. And I put that in for f sub t. I put s over n into that formula and stick it up in there and take the inverse Laplace transform to find out what f lambda looks like. Now, a couple things about that. Okay. So I put this preferred choice in there. On this first line on the next page is that exponential stuff stuck inside there in this inverse Laplace transform operator from the S domain inverted back into the lambda domain on the right-hand side that I need to evaluate. But what is in there? What's in there as a function of S? One thing is e to the minus beta over n times S in the numerator. And there's a step function, and then there's a power of S in the bottom. And in another paragraph, maybe shortly thereafter, I show that if I assumed, which I don't think is correct, but if I assumed instead of an exponential, a delayed beta distribution, a delayed gamma distribution with some parameter, that this formula hardly changes. You just have to replace certain ones by k's, where k is the number of exponentials that you added up to form the gamma. So this is really at the heart of the problem. I'll just leave it here for this case. So the first thing is that the theory of Laplace transform lets us take this. This is not the first thing that I did, but I guess maybe I'll point out the first thing first because it's simpler. Oh my goodness, I'm not sure that I have it in there. First thing you notice is that there's in the transform domain there's a e to the minus beta over n times s. This corresponds to a delay of beta over n in the inverse domain, which in this case is the lambda domain. From the point of view of neuroscientists, and a couple of them present, this result is amazing. This result tells you that the intensity never falls to 0. And I didn't build it in, but it tells you that. And this is widely observed in all families of neurons. They all spike. They're all excited all the time. Maybe very lowly excited and only spiking once every minute or so. But they never don't get excited and they never don't spike. unless they're dead. So that happened here, even though I didn't build it into the model. It's actually effectively, when you get the answer, much more, that's where it went really to 0, but it's damn near 0 for quite a long time above that as well. Okay, so, but that's very nice to know. And then the next thing that, and of course that means that you can drop the e to the minus beta over ns out of the whole calculation, get the answer, and then shift it back by that much. So we just leave that out from now on. Okay, now, there's the step function. What do I do with the step function? By this time, the step function is in the S domain is happening at nd, which is a pretty big number, because n is 10 to the 4th, and d is small, but, you know, it's pretty big. Well, it turns out that the step function, if I'm doing this right mathematically, and this is recent that I found this out, so if anybody disagrees with it, I'd really like to know. But it turns out that the step function is totally irrelevant, and you can just remove it. And you know that, if you look for a little while, because you took your circuit theory course a long, long time ago, you learned about Laplace transforms. And you learned about the inverse Laplace transform contour. And the inverse Laplace transform contour is a vertical line in the right half plane of the S plane when you make it complex. And the only requirement on that line is that it has to be to the right of all singularities of the thing that you're transforming. You can take it any number that you want to the right of all the things that are transforming that is single singularity. Well, there's only one singularity of that thing. It's a pole of order m-1 right at the origin. There's nothing else. And the e to the minus term is gone also, and not that it had any singularities in it. That means that all I have to do is to push that contour out to the right, facing you, in S, in the real part of S, until it gets past nd. And now the unit step function is 1. And I take it there. And the unit step function is gone. So that's what I do. Okay? So now, you really don't do that. It looks like it's a problem, but it's not a problem. Okay. And so, yeah, this next thing in the bottom here was just saying that I could have, instead of assuming the delayed exponential, I could have used the delayed gamma distribution. Not mathematically, it wouldn't have gotten more complicated, except I don't have the same justification for using that I do for the exponential. So I remove this unit step function. And then I deal with the factor of that I already did for you in the second paragraph here. Says, having removed that step function, then we get rid of the exponential by shifting things over. And finally we come down and we now take this inverse transform. And that's not very hard to do. If you want, you could say it's s to the m-1. You can look it up in the Laplace transform table. I didn't do that. I just sort of integrated the delta function m-1 times the transform of that, and it produces this. Because every time you integrate, you know, you get another s down in the denominator. So delta functions start out constant. You iteratively integrate n minus 1 times, and you get f sub lambda. And there's f sub lambda. F sub lambda of lambda, some constant that I'll talk about in a minute. M minus 1 over n. M is the number of spikes that have to arrive, afferent spikes that have to arrive before it spikes. N is the number of afferent neurons. Beta, which is I'll talk about beta. That was just, at the moment, it was a number that I put into the exponential distribution. I said that to be energy efficient, it had, in the long term, it had to have that exponential. But I know what that number beta is. All you need to tell me, for me to give you that number, is how much more it costs for this neuron to spike than for this neuron to stay quiet and just be doing it. Once you know beta, you know. Once you know that ratio, then beta is a direct function of it. That's known. So you can consider that beta is known. And then you get lambda minus beta over n to the m minus 2, lambda to the minus m. And now I take that function and, I left out the, I didn't leave out the unit step function. I started it at beta over n, and then I chopped it off at 1 over d, because really per neuron it can't be bigger than 1 over d, and that's why you have to adjust the constant in the front so that it integrates up to 1, which is not hard to do. I don't know if I did it on here, but I have that integration also that gives that constant. So, anything more there about that? I don't think so. Just want to talk about this thing a little bit. So, at least for this analysis, I don't get the kind of thing that you were talking about where sometimes it's 0 and sometimes it's 1 and it's never in between. It's very much in between. But in fact, it's never 0. And it has an upper limit because of the refractory assumption that I put in things that doesn't let it get bigger than 1 over d. It has a shape. The shape looks something like this. I don't know that it came down to 0. Probably didn't really come down to 0 yet. There's a 1 over d. No, that's right. It did come down to 0. No. Well, it looks something like that. And it's near 0, but it isn't really added at 1 over d. So it's some shape like that. And 1 over d is in here somewhere. Now this is, this part is very much lambda to the minus 2. And this part is very, very small. And this is the s over n, which is the n over s. This is the beta over n, which is a very small number. And in here, it's really lambda minus beta over n to a number which is quite large, because it's m minus 1, m minus 2, I guess. And m tends to be hundreds, a couple of hundred spikes that it takes before the thing, anything arriving before the thing spikes. So this is very, I'm just writing 200 here, but this is 100 or 200 or something, this thing. So it really takes it a very long time. This is where it's absolutely limited. It never goes below that, but effectively it really comes out so that that's too low a number if you look at what goes on. But the math is really telling you that you'll almost never see anything in excitation rate even above that by several multiples. You have to go many multiples of this thing over to the right here before you really begin to see it come up. Then it comes up pretty sharply, and then it dies down slow and disappears at the end. And so this Laplace transform theory was put to work, and actually to produce this answer, which I believe in very much, and though I didn't build it in, I got the fact that neurons are always excited. Just without building it in there, it took place. Which further, well, I was going to say further leads me to think that the exponential thing is correct, but I guess I can't really say that because I would have gotten that with the gamma also. So that wasn't a function of so much of the, well, it was a function of the exponential that was in the Poisson thing. That's what it really was. The e to the minus n lambda s is what led to it. It's in the Poisson process. Okay. So is the bombardment process Poisson? And the answer to that is definitely no, even though I said it was a very good approximation. But it's got to be no, because it has after effects. Because again, you can't have more than n spikes occurring in less than 1 over d. And you know, a Poisson process has no limitation like that. So that's one of the ways in which the Poisson approximation breaks down, but that's on a very fine-grained time thing where I don't think it affects the rest of what I've done here. It isn't genuinely Poisson, but very well matched that way, usually considered to be that way. Okay, I probably ran over by 5 minutes or something. I don't know what the time limit was. Okay, so that's it. I will make sure that you have in the electronic version that you can bring home not only the 2 things that I talked about this afternoon, but also this appendix that has this information about why that has to be exponential.
Okay. So lunch starts now at 1:30. We start with the panel.
The 3 divisions are the past, the present, and the future. All right? So let me go ahead, and of course everybody knows the panelists, Toby Berger, David Shea, Muriel Medard, Gerhard Kramer, and I'm going to be moderating. So let me... Muriel took notes, so that's proof that they did receive the questions before. So I'm just going to ask them to briefly introduce themselves, and the first part of the questions are, what were you doing as a PhD student or postdoc? What did you plan to do, and what did you end up doing? And I'll start on this end.
I'm supposed to say what I plan, what I say once again.
pass
Introduce
the.
yourself. Introduce me. That's what I can do it.
Okay.
Okay, I'm Toby Berger. I'm from the University of Virginia in Charlottesville. And there I work on and teach communication and information theory. And I've also been carrying on a collaboration in trying to work on the interface between system science, especially information theory, and neuroscience on and off over the last 10 years.
No, there were some more specific questions, I think. Don't try to pass it so quick to me.
Okay.
That's okay.
Introduce themselves. What were they doing as PhD students or postdocs? Me, you mean, as a PhD student. Okay.
So that's the past part.
I worked with Don Tufts, who at the time was at Harvard and now is at the University of Rhode Island. We had a group of people who worked on communication theory problems of the time. He himself had done work in pulse amplitude modulation systems, and so like some of his other students, I worked on extensions of that. And some of my extensions had to do with comparing the performance that those systems achieved relative to bounds from information theory about the best kind of mean squared error or probability of error that could be achieved in sending the data in question over certain sorts of channels, and you could do it by this pulse amplitude modulation, but that of course wasn't the best thing, and so we wanted to see how far short of best it was. To do that, there was this subject called information theory, and you had to learn something about that. And once I started learning about that, I knew that that was what I wanted to do more than the communications, so that's what I've been doing ever since. Okay, what did I think I would do? Well, that depends on, I mean, when I was a PhD student, what did I think I would do? Well, I was supported in my PhD work at Harvard by Raytheon Company under a Raytheon Company Advanced Study Fellowship or some such name, for actually the whole time that I was at Harvard. And so I assumed that I would go to Raytheon and work for Raytheon, which I did do for 2 years. On the other hand, even before I did that, in the back of my mind was the feeling that I would probably go to academia at some point, because I didn't think Raytheon, well, I knew Raytheon didn't have much use for information theory. So I did, in fact, do that. I went to Cornell University after about 2 years at Raytheon. One thing about the Raytheon program, or if ever you get to the point where you have a big enough company that you can set up a program like this to send some of your promising young people to school to get advanced degrees, you have to do one thing, which is very difficult. They have to be sponsored by a certain group within the company, of course, and put forward in some sense as candidates. And the rule ought to be, but isn't, that when they finish their PhD work, they come back to the company in any group but that. But of course they didn't have that rule. And that's the reason is, you know, that once you go in there and you work like I did for 2 years, 3 years with these people, there's certain relationships that are set up, and those relationships cannot be done. And the fact that you've got 2 pieces of paper in the meanwhile that says you're a master's and there you're a PhD student, still you're the new guy on the block relative to them, and they just don't look at you that way. Whereas any place else in the world that you worked, even in the same company, is the place that you should be sent to. So that was part of it. They treated me as nicely as they could at Raytheon, but they couldn't overcome that problem either. So I both plan to, you know, give them back some of my time for having paid for me, and if I liked what I was doing there enough, I suppose I would stay, but in my feeling was that I probably wouldn't. What did I do? Well, I guess I just told you what I did do, so now I can pass it to David.
Okay. You could hold both of them, David.
Both of them?
Yeah. There's or I'll hold it if you like. 'Cause this is for the recording, and that's for the.
This is for the recording.
No, this is for the recording.
Oh, but this doesn't work.
No,
That's okay. People can hear me, right?
Okay.
So, what was I doing? So this is a tough question, because I wasn't doing much. Because as
That's not true. We
So PhD student, wait, I'll get to you in a second, Muriel.
It's such a high threshold for much that it may seem that way to you.
Sounds like an embarrassing question, set us up to do something here. So PhD is the greatest time. You can sit around, socialize with your fellow office mates like Muriel, and have a good time. You don't have to worry about grant proposals, committees, and so forth. Really a good time. And we had a great time, and I was a student of Bob Gallagher and John Sosiclis at MIT, and we were in this lab called LITS, Laboratory for Information Decision Systems, and I shared an office with Muriel, with Emre Talatar, and other people, and we had a great time. Okay, so that's it. But I forgot what I was doing as a PhD thesis. Completely forgot. Can't remember at all, so never mind about that. Okay, what did they plan to do? I wasn't planning anything. I was just hoping to hang around longer in this place where I don't have to do anything. But one day my advisor said, look, I don't have much money for you anymore. You better get out of here. So I said, oh, okay, so good days are ending. And so I applied to academic jobs. Fortunately, I got one. And then I deferred that for 1 year, and I went to Biolabs to do a postdoc, and that was a good thing. Because after my postdoc, I completely changed my research direction. And I've been to Berkeley ever since.
Can I take those?
So what I was doing as a student, well, I started out actually in optical networks in my master's, working for Bob Kennedy. I was his last student. I don't know if I made him retire or not. But there I was, and then I said, okay, I have to find another advisor. The last one, just couldn't take it anymore. So I looked around and I was talking to various people. At some point I thought even of maybe going to OR because I really liked optimization. And then I finally decided to do something more in optimization, but in the wireless domain. Wireless seemed like it was really interesting. And I remember talking to Bob Gallagher, and he told me, oh, you're in optical networks. It's a really hot area, very interesting area. Why do you want to change? And I said, no, I think there's something good here. He's like, okay, finally, he said, okay. And then I decided I wanted to optimize something, so I figured I'll just go and get a problem to optimize. So I'm running around looking for problems to optimize, and
yes, she was running around.
I was running around. You remember that? I was running around. So I was running around looking for problems to optimize. And I thought, I had taken information theory, but I thought it was fun, but frankly, I thought, well, I'll never see that again. Because I thought I was going to go to industry, and I thought of myself as somebody practical, and I wasn't going to keep doing this. So I was looking for problems to optimize, and finally I said, well, we don't optimize capacity. And of course, what was happening is that the capacity that was known is basically the Alsfady, Kobe-Weiner region, and that there was nothing to optimize as far as I could tell. But then I started getting intrigued as to why people thought that the channel was invariant, and I thought, well, how do they know the channel? Who told them the channel? How did these guys find out about the channel? And so I thought, okay, I'm going to spend just 3 or 4 months to figure out the capacity under this time-varying channel where you have uncertain information about the channel. Well, that turned into my whole thesis. I never got to optimize a darn thing. And I came out, and here I was with an information theoretic thesis. And what did I think I was going to... so by the way, what else I was doing? I was obviously having a fantastic time with my office mates. Having great discussions, but I was also starting a family, and I was also an aerobics instructor. Actually, I was a physical education instructor at MIT way before I was a professor, and also being very active with my sorority, which at first might seem like maybe it's not that useful, but in many ways taught me a huge amount of skills, or at least I hope they're skills that have been very useful down the road. So what was I planning? Well, actually, when I said I was planning to go into industry, frankly, I didn't really have a plan. And we'd have these discussions with my advisor of like, well, what are you going to do? Like, I don't know. And that was pretty much You know, I mean, remember, I didn't know what, I really didn't. I
Yeah,
figured
our
I would,
advisor is not a very particularly organized person either.
yeah, that's right. So anyway, we would have these discussions, and I remember one point he said, well, have you thought about academia? And I said, oh, absolutely not. You know, no way. You know, I've looked at your job, and I don't think I want it. Because, you know, it seemed like such a high-stress type of gig. I just didn't see myself doing it. So what happened is, so I graduated, and my husband had been in the armed forces, and he decided to separate from the armed forces, not to renew, and instead go back to graduate school. And we had a child, and so instead of being a housewife, which was one of the career options I was considering, I thought, well, somebody has to feed the kid. So I thought I should work. So that's why I went to work. So I interviewed 2 places within a 10-minute radius of the daycare. Sorry. Well, I mean, you know, maybe this makes you feel better about yourself. And I found I had several offers. From BB&N and from Lincoln Lab. And I had several offers from Lincoln Lab, and I took the only offer that had nothing to do with my PhD thesis because I thought, well, I'm only going to be there for a couple of years while my husband finishes up his MBA, and then who knows, you know, maybe I'll stay at home, maybe we'll move, right? So I want to learn something new. You know, I want to do something fun. If I'm going to work, it might as well be fun. And while I was there, I started working with students. I started working with students because you could supervise master's students from MIT. And I was completely hooked. I thought this was just the best thing. I mean, supervising students and working with students was just so amazingly good. I had not expected it to be good. I mean, seriously, I mean, it was, you know, I mean, I liked them fine, but it wasn't something that I realized I really loved to do. And I found this out. And I remember the reason I went into academia is actually I was talking to Andrea Goldsmith. I was visiting her, and we had some collaborations going. I was visiting her. She was in Caltech at the time. And I remember we had been talking, it was like up until 1 a.m. And I said, Andrea, you know, I'm not quite sure what I should do. You know, should I continue working? Should I, you know, what should I do? And she said, well, have you considered academia? You know, it sounds from what you're telling me that of what you like in your job, that that's really where you would be best served. And that's how I went into academia.
Thank you. So for me, I did my PhD in Switzerland, but I was coming from Canada, so that was a little bit of a change. Some people ask me sometimes why I went to Europe rather than somewhere in the States. And it's really just because of my German background, and I wanted to go either to Germany or to some German-speaking country to have a different kind of experience, to do a PhD somewhere else. So I wound up by some luck, I would say, with Jim Massey at ETH in Zurich. Basically, I wrote a letter, and then I waited for a long time and heard nothing. And I thought, oh, this is probably, nothing's going to turn out. And I think it was then on Mother's Day in 1992 that he phoned me and asked me if I wanted to come over for an interview, so I did that. And what I started working on first was cryptography. So I was looking at cryptanalysis, but I rapidly got turned off by that. And the reason is I always thought, well, if you try to cryptanalyze a cipher, people look at 2 to the power of 50 or 40 plain text ciphertext pairs, and I couldn't figure out why the heck this could ever be practical. So in some ways I was demotivated because of the lack of, what I thought was the lack of practicality of looking at problems like this. So I decided to switch, and I got involved with a project from with the PTT in Switzerland, so Swisscom, and started working on something called CTDMA. Did that for a while, and then with about 2 years left, or I had already been doing my PhD for 3 or 4 years, Jim Massey asked me, what topic do you want to work on? And I said, well, I want to work on multi-access channels with feedback. He had suggested that problem to look at, so that's what I did. Towards the end of my PhD time, I really had no idea what I wanted to do. I wasn't sure whether I wanted to do academia. I kind of thought, well, maybe I will do that eventually. But in the end, I wound up at a small company, at the time, 2-man company. I was the 3rd person. When I started, they had no money. And so it was a very large change, going from PhD where everything was taken care of, and then all of a sudden joining a small startup where you didn't know whether you'd be earning money 2 months from now or 3 months from now. And this was on a continual basis. In fact, at the beginning, my 2 colleagues, the ones who hired me, they had to not pay themselves for a while because they had to legally pay me since I was the first employee of the company. So it was a very interesting experience, and I did that for 2 years, but I rapidly knew I didn't want to continue doing that for a variety of reasons. And then I applied for 2 positions, one at IBM in Rishlikon and one at Bell Labs in Murray Hill, and I got both offers and decided to go to Bell Labs. And that's where I've been since then.
Well, I didn't want to answer these questions. That's why I volunteered to be the moderator. One thing that seems to be coming across is life brings you a lot of different things, and you often don't know what you're doing. In my case, I still don't know what I'm doing. But and then things quickly change, and it might change in a way that's all going to work out, it seems, at least from the group here. So if you have any questions regarding this part, the past, we'll take them now. Any questions about their past that are related to academia?
We're being recorded.
Appropriate academic questions.
Appropriate academic questions.
Other questions you can ask offline, maybe. Lalita.
Well, at least to some of you guys, was the academic job market as bad as it is, or as challenging as it is now?
Anyone who would like to?
I think when I was in graduate school, it was much worse. It really was. And I think when I started looking, it was getting on the mend, right? But I remember when we were in grad school, remember when we were starting out, it was dismal. I mean, I don't know.
I guess we don't want to ask.
No,
How was the job market then?
Let's see, how was the job market? Well, I didn't really contend with it because I had this Raytheon thing set up for me that I had to go back to. So it didn't really occur to me. I wasn't looking for an academic job directly. As I say, it was in the back of my mind. And about 2 years later, I just sort of got recruited into it, which I guess means that the academic market must have been pretty good, but it wasn't like I went to a lot of places looking. Friends of mine who were at Cornell, one of whom was a former graduate student with me with the same advisor, just tried to make me interested, and they succeeded. So I don't have a good answer.
I think job markets are kind of cyclic because when we were grad students, the market wasn't very good. I remember one of my friends, a year ahead of me, also Gallagher student, he applied to 50 jobs, and he got 1 interview and 1 offer. So yeah, these are cyclic. I think in the late 90s and early 2000s it got better, and now it's a little bit on the low side, but I think these are cyclic. So.
Okay. So this is actually tying into the next one very nicely. So we're going to talk about the present now. And we figured that we'll ask questions that you might be interested in, which seems you are. First question is, if I was a grad student or a postdoc just about to finish or maybe a year ahead, should I try to find an academic job or an industry job? And also a second question is, what kind of job can I get by studying information theory? And that's from all the graduate students. And I'll start at this time from here.
So those are questions for the students, huh?
For you.
Of what you want to study.
This question for us.
That really,
We're asking you.
First of all, it depends on you, of course, what you're interested in. I know a lot of people who they do their PhD and they like to do research, but they just decide, well, yeah, academics is not for me, and it's not. And they go into industry and they do really well. They might wind up in research, they might wind up doing something completely different, but they generally say they like their time doing a PhD. And so it's really up to you what you do. I mean, I personally was very glad to have gone through a period of time where I was doing a small startup and now sort of Bell Labs isn't really industry as such, at least where I was. It's more of a sort of quasi-academic environment. It used to be even more academic. So from that perspective, it wasn't as much of a big company as many other places. But I was very glad to go through that experience because it's the variety that makes things interesting, I think. Seeing many different things, seeing the challenges other people have to go through is very valuable to your own growth. And I think you should just try to look for something that maximizes your own growth potential. And that doesn't just mean working on certain mathematical problems, but really understanding your fellows, understanding what they do, what they go through, and that'll help you in your career. And when you're starting early off, you have the opportunity to do this because it's very forgiving. You have the chance to do something for a couple of years and then switch and do something else. And I think just take advantage of that. I mean, the world offers you enormous amount of opportunities. There's really a lot you can do. And the second question.
What important topics, what to do, what kind of job?
What kind of job?
What kind of job can you get with information, doing information theory? Well, that kind of goes into what I just said. I mean, you can do anything you want. You can't necessarily do information theory first, right? So there's certain limitations there. I think the number of jobs you can get is limited there, and so it is very competitive. All of you guys are, not all of you guys, but a whole bunch of you guys want to get academic jobs, and it's not easy, right? Because there's a limited number of jobs, and you have to take that into account, right? There's a limited number of very specific kind of jobs, but there's a whole bunch of other kind of jobs out there, and they're all interesting, and you can make them interesting. You make them interesting for yourself. So I guess that's what I'll say for now.
Yeah, so I guess important topics. I think the topic is important if you think it's important, right? I mean, really, it has to be something you believe in. It has to be something that when you explain it to other people, you get excited about. Just because it's a hard, open problem doesn't mean that it's important to you. So I think you have to feel very much like you're in charge of that and that it's relevant. In terms of what to do, I think if you just do good work and you're open-minded, I mean, I know I'm going to sound like Pollyanna, but things often do work out well. Not always in the ways you expected. When I went to my first job at Lincoln Lab, I was obviously not doing information theory. As I said, I wanted to learn something else. So I was working with people developing really fantastic all-optical networks. And I was just working with some of those amazing applied physicists and learning a ton. I mean, I was just learning so much. But the skills that I was bringing from information theory were maybe not exactly, that impressive. I remember one time, they were trying to put a code on some channel, and I ran some simulations. I had a curve, waterfall curve, and I showed it to my boss. He's like, "Wow, that's great!" I was like, "Well, actually, it's not that hard." I was like, "Yeah, right, it's great." For an information theorist looking at that, I was like, "Well, any information theoretically information theoretically trained monkey could do this, right?" But again, I was learning a lot, and it didn't prevent me from sort of going back to information theory later in my career. A few years later, when I decided I wanted to re-engage in that. So what kind of job? I think it depends a little bit on how you think of yourself. I fundamentally think of myself as an engineer, right? So if you think of yourself as an engineer, then you see yourself as teaching engineers. That doesn't mean that it's a trade school. I don't see engineering that way. I see engineering as being just as noble a pursuit as philosophy, history, or any other of the maybe traditionally more highbrow type of disciplines. And so I think I see my role as training people who are going to be engineers, and I expect that many of them will be interested in going to industry. And some of them will be interested to go into academia, but it has to be that they really want academia, not just some perceived prestige, which is maybe within this community, but maybe not outside the community, right? Actually, if they want to do something completely different, that's fine. I mean, some of my students come to me and they say, I want to go into finance. And they often have this slightly shameful look, like they tell me, I'm going to join the circus. And it's like, I tell them that's great, that's fine. I mean, what you have learned is you have learned to think critically and to go back and forth between mathematics and reality in a really relevant way. And if that's the way you want to apply it, go for it. So I think, in the end, it has to be something that works out for you.
Yeah, so I agree with everything that Muriel has said. Always.
Nothing to add?
Yes, so I think, as I said, a graduate school is probably the best time of one's life, not only because you can socialize with your friends and family, but also because you can pursue what you're really interested in. So I think that you should really take advantage of, and in the process learn something useful. As Gerhard said, there's no guarantee that you'll be doing exactly the same thing as you were learning in graduate school, but so in the process, hopefully you can try to use the graduate school time to broaden yourself, to learn as many things as possible, and to do one thing deeply, and I think you will carry along with that for the rest of your life, and useful. Yeah, academic and industry job, I think it's very hard to plan for that, so I think follow the flow. Academic jobs, there are not that many around, but so what else questions do I have to answer here?
What kind of job can I get by studying information?
Okay. So I think information theory, I think one of the best thing about information theory is, as Muriel said, it's not only mathematics, but it's really a connection to an engineering domain. And so I think if you can learn not only information theory, but the intimate connection with the engineering domain and how to think about modeling problems, be they biological problems or wireless communication or networking problems or pattern recognition problems or learning problems, I think you will benefit. I think that skill set will be very useful for you, whatever you do.
Okay, I'll get the list of questions in front of me here and see what I can add, if anything, to these many marvelous remarks that have already been made. Should I try to find an academic job or an industry job? And what kind of job can I get by studying information theory? Well, let me start with the latter. I think Ireland said that, Gerhard said that at some point you were going to answer for me, for the panel, what it is about information theory. My question: what is it about information theory that's different from all other subjects? So let me see if there are any other takers out here to give the answer to my annual question. That's the same response I usually get from my class when I ask the question.
There is one up there.
There was someone there?
I know the answer because I took your class, but...
That doesn't. I know it too, but it's not that.
So, I usually get, if I get anything, it's something like this. They say, well, this course uses an awful lot of inequalities, and in most of my other classes, there's mostly equalities and only occasional inequalities, and this one is very much the opposite. And I say, well, that's true, but that's not what I'm looking for. And then somebody says, maybe, well, you prove a lot of things. You spend time proving this and then proving that, and then we do some of that in the other courses, but not as much. And I said, yes, but no one gets the answer, and then I have to tell them the difference is that information theory is beautiful. And of course, this is what I'd like you to try to keep in mind while you're going in whatever direction it is that you do go with your your future careers. I think a big part of what makes it beautiful is the thing that other members of this panel have already alluded to. I'd like to add to that information theory, let's say Shannon, in founding it, found a way to take this theretofore previously mushy concept of information that was nonetheless central to ordinary conversation and to the way in which a lot of sciences in physics and in biology particularly thought about things, and somehow quantify this in a powerful way that continues to this day to find more and more things to apply it to. So in some sense, although information theory is over 50, I guess more than 60 years old now, it's still very, very new in the history of mankind that information had any kind of quantitative definition to it. So you're still early on in this, and you shouldn't take the point of view that that all the good work has been done and there's not much left, even at the fundamental level. I think there's a lot left that you can find. What kind of job can I get by studying information theory? Well, that's worded in such a way that I think that the answer in 2008, and actually forever since the whole last 10 years, has been that there's no job that you can get by just studying information theory anymore. You need, while you go through school, to study something else as well. Wireless communications, multimedia, economics, biology, something that can conceivably use information theoretic ideas, because it used to be that there were a few high-level laboratories, Bell Labs especially, that were hiring in large numbers, and they were interested because they had information theorists there, and bringing in a few new information theorists every year or two to see which ones of those, to give them a good experience and perhaps to keep some of them on. It's not clear that there's any laboratory in any company right now that can afford that luxury. So even in industry, so in industry, you've got to be able to do something useful right away, and then they'll tolerate you're doing the information theory at the same time. But I don't think you can just come in and say, I am an information theorist, nothing else. I don't want to work on anything else. I don't want to be concerned with what it connects to. That was not necessarily previously the case in academia, and as far as your research is concerned in academia, it's still true. However, to get that academic job, you have to train all these other people who have to go out into this industry where they need to be pretty immediately useful. And that's true of almost all of your PhD students who will not, in the main, get jobs in high-powered research places that can afford to have a bevy of information theorists on the faculty. So you need to get taught, you need to become an expert in something else that you can teach as well as the information theory course, so that you fit in to the academic institution, not on that one narrow thing that I think it's very hard to get a job on just studying information theory and not anything else. So you want to tie it together. That's been alluded to already, but that's another reason why you want to do it. David has mentioned a couple of times that being a graduate student is a wonderful time of life. I don't know that it necessarily feels that way while you're going through it. It's something that it's very easy for David and the rest of us to say after we've gone through it, and it's not because the future part of your life is so awful, but you suddenly appreciate in a better way than you probably did at that time what a special kind of type of freedom that you capitalized on some components of, but you weren't really aware of it. So I would like to add to that what you should do, if you possibly can, in your last year in graduate school, for those of you who are still in graduate school, is to get everything pretty much done on your thesis, but not spend that last year writing up 4 different articles for all these journals about all these chapters in your thesis. But instead, maybe do a little of that. You've got to put some articles out because it's kind of competitive now more than it was when I was in school. You need a kind of a list of publications in the CV that's sort of lengthy. You should certainly keep going to the conferences and get those publications. Don't push yourself too hard to turn out all these journal papers. Spend that last year working on something that's damn hard, because you're never going to get the chance again until maybe after you get tenure, if you succeed in getting a job in a place that, I guess after you get tenure, you can work more on what you want to work on without having to worry about whether or not there's an answer coming out soon. But this is another period in your life when that's true, and you can try something very challenging and at no consequence if it doesn't work out. And if it does, then it opens up, great doors for you, and that's nice. It's getting harder and harder to do. The certain escalation process here has made it difficult to do anything other than build your resume, even with your last year in graduate school. I think that's unfortunate. Try to resist it. Should I try to get an academic job or an industry job? Well, that of course depends on your orientation. I guess I'll rephrase that question. If I'd like to get an academic job, should I look for an academic job and an industry job, or just try to find an academic job? I would say you should spend your first attempt at this looking at maybe a small number of prestigious engineering institutions that have research laboratories and try to get an academic job. And if that's not panning out, which in many cases it does not, well then you broaden your horizon somewhat.
Thank you for all these very nice comments. Before, I guess, we take the questions, I expect quite a few questions in this part. Let me just quickly say that I totally agree with you need to do what you want to do, and you won't be sure of what that is during graduate school or maybe during postdoc also. Sometimes it helps to spend a few months in one summer at a company because it can tell you whether you can use these fundamental skills that you've learned and be useful for that company or that kind of a job. I've done that one summer. It was a very important and valuable experience. I learned a lot about practical aspects of wireless. I also learned that that job wasn't for me. So that's also an important finding, I think. So with that, we'll take the questions from you. Go ahead, please. Lolita.
Oh, this is for Professor Berger, actually, or maybe a lot. So you said maybe you should combine information theory with something else if you want to get even an academic position, say biology or something. By the same token, there were comments like maybe you want to be narrowly focused when you're either a postdoctoral fellow or on tenure track and do other things after you get a tenure position. So that's a bit confusing, at least to me.
I wasn't saying that you shouldn't do the information theory, but I was just saying that maybe what you want to do there, because it's one time in which you can do it in your life, is to try to formulate something. I don't know, find something and try to look at it. I don't want you to be Shannon, but to try to look at it in that spirit, and ask yourself broad questions like, what is information? How do I measure it? That's kind of the things that he thought about, questions that somehow nobody had really even dared to try to ask in a mathematical and scientific way before that. So I just think you should try to look at something that's been of long standing, or something that's just so creatively new that it's not clear it's leading anywhere, but it comes out of your head, and you should just give yourself the better part of a year to try to do that, rather than to continue refining and extending some papers that you wrote that resulted in your getting a PhD. It'd be nice. For me, that was a wonderful period of time. That 1 year, it was sort of the last half year I was at school and the first half year I was out. I felt that I could try to think about some things in a deeper way than I had previously done. I did some work on the book on rate distortion that I wrote, and I even had something in there about biology way back then. So that was one of the ideas I looked at that point only briefly. So I don't know if it's contradictory. It is, I suppose in some sense it is, because this is saying, well, here's all these pressures on me to build this resume and go out and get this job and be just what the people who want to hire me want me to be. But if you can succeed in also being something else that maybe they don't even know about yet, that they can admire, that will be better still. That'll probably carry you further. It's not easy to succeed in that, of course.
I have a question maybe for each of the panel members. So I was wondering if each one of you had to go back to school and do their PhD, what kind of things would you be looking at?
Oh, that's a good question. What would you be working on now? Yeah.
Well, I have to kind of decide whether I should say back then or now or something.
Now.
Now.
Yeah.
What now? that kind of goes into the next topic, I guess, too. Well, tough to answer that question. In some ways, it depends a little bit what's going on at the place where I would be. I guess I don't know. I mean, that sounds strange, but it's true. I don't have any specific topic in mind. I mean, I'd do what the things that interest me now is the easiest thing for me to say. It's hard to say anything else. So I'm interested right now in multi-user information theory problems. I love the variety that I have there and everything that it connects to, both from the low levels to the high levels. I mean, maybe it's a simple answer. I don't know. I would do what I'm excited about doing now. And that changes over time. I was interested in doing cryptography at the beginning. And I was interested in it because I read a paper of Jim Massey's, which was really beautifully written and understandable for a student who is not even doing graduate studies yet, and I was really interested in that. But then that changed over time. I don't know what more to say about it than that. I'm not sure if that is what you
Well, I guess,
hope it was.
I mean, of special interest would be something that maybe you're not working on right now.
Well,
Because that's obvious,
yeah.
right?
Well, okay. So if I had more time and energy, there are certain problems I've gotten involved in at Bell Labs that I would start pursuing a little bit more, and that's information theory for optical channels. I'd like to learn a little bit more about quantum mechanics if I could. At the moment, I don't have that much time for doing things like that, and I have other priorities. So these are sort of second and third tier interests already. It's not as if they're the first tier interests.
So I can tell you the algorithm I followed to choose my topic, and I think I would still keep the same algorithm. When I was looking around as to where to apply and what to do coming out of undergraduate, I had triple majors in undergraduate, which sort of shows again my lack of decisiveness. And I knew that I mostly wanted to work with a group of people that was smart and nice. And that's how I chose. And frankly, I'm sure that I would have been perfectly happy doing circuit design. I'm sure I would be perfectly happy doing quantitative chemistry. I really do, right? And I think it helps to think of yourself that, I mean, I love information theory. Obviously, I'm very invested in it. But I don't want to think that this is the only way in which I can contribute to the larger academic effort, right? That if I was doing something else, I would still be happy. And I think it's much more important when choosing a topic to choose a community and a set of people that you're going to work with, particularly who your PhD advisor is going to be, and to feel that you have a real rapport of mutual respect, and that you're getting the support and the freedom that you want. So, right now it would depend on what graduate school I was at and where I would go. I never certainly did not go into graduate school saying, oh, I need to do information theory. And I think the problems evolved out of discussions with my advisors and also with a lot of my friends, and taking classes, as Toby was saying, outside my, what would be considered my field now. I took quite a few classes outside my field, which very often in the end I did end up using in some way, shape, or form. Does that answer your question?
Yeah, kind of. I mean, I guess the reason why I asked this question is because you are obviously very famous, you are influential in the field, you know the field very well. So you have a very good perspective in as to what is important, what should be pursued. I guess that's why I asked the question.
So I think maybe what you're asking is if we were to go into information theory right now as grad students.
Exactly.
Ah, okay.
The knowledge that you have right now, of course.
Oh, well then I'll give pretty much the same answer as Gerhard. I would do what I'm doing now.
You have to find what fits right for you.
Yeah, it has to feel right. I mean, right now, I'm very interested in the network coding just because for a long time I felt like I was leading this double life in networking and in information theory. And I remember a funny thing with Tom Chen at SMU, who knew me from my optical networking work, said, Muriel, it's so funny, you have such an uncommon name, but I saw that somebody with your same name working in information theory. Like, there was a paper at this one conference, and Tom, that's me. He's like, no way, what are you doing? It was like really like, and so, I felt like I was no longer as much leading. I really sometimes felt like I was leading a double life, right? And so for me, it was nice to bring those two things together. Things that you're interested in. Again, because I think of myself as an engineer, I really have to feel that what I'm doing is benefiting an engineering problem. I feel that way about network coding. I feel that way about a lot of things in wireless networking, and started doing some work with the Broad Institute in genomics and proteomics, and I feel that way there too. I feel that they have real problems that we can do things with.
So I guess you're looking for a thesis topic, right? It'll cost you. Actually one thing I find interesting about information theory is if you look at the title, it's information theory. And in some sense, our whole world is about information. However, as a field itself, in some sense, the problems that we look at, I think, are relatively narrow. A lot of the problems we looked at are very specific to reliable communication from one point to another point, or from one point to many points, and so forth. So in that sense, information theory, I think, as a field, a lot of the research has been focused on relatively narrow range of problems. And I think an interesting direction, which I think is alluded to some discussion this morning during Professor Berger's lecture, is sort of how to start thinking about communication not as an end goal, but as a part of a bigger system to accomplish a higher level objective. And therefore, that will give you a sort of a more external perspective to information theory, how it interacts with the rest of the system. So this is an age-old problem a little bit about information, the syntax versus the semantics issue. I think we have been focused on following the lead of Shannon, really, as focusing on the syntax, because he said in the first page of his 1948 paper is, I don't really care about the content of the information. I only care about the fact that information is a bunch of possible messages, which I want to convey one of them to the receiver. So I think once you have to address high-level problems like control or decisions, then you have to start thinking about semantics of information and how the reliable communication gets tied in with our problems. And that's where, for example, feedback becomes a very important thing. So feedback is obviously a very intriguing topic, but I must say, in terms of information theory as a whole, it has not made a huge significant impact. And I think the real impact comes in when you tie information theory, tie communication to other problems like control or computation or making decisions, etc. And I think a field like neuroscience that Professor Berger talked about is a really a good area in the sense that it's like communication in pre-1948, very amorphous. We don't know what the central problems are. It really takes a information theorist mindset to try to focus and find the essential, or at least any essential aspect of it, and try to make some sense out of it. And I think this morning's talks already suggest some possible directions there.
Yes, it's a pretty long-standing problem to try to look at the relationship between information and control. Even before or around the time, let's say, that Kalman was doing his fundamental work, and after he completed it, and up until recently, the view in, say, the Kalman formulation had always been that although there might be a very large multidimensional observation vector, that by some miraculous means this multidimensional observation vector was instantaneously available noiselessly, other than the noise that had corrupted it at the points of observation, to the person. It was noiselessly available to the person who had to determine the controls to apply on the system using Kalman theory. There was no delay and there was no inaccuracy caused in the communication that went about that delay. But of course, life is not like that. So if you're NASA and you're shooting up a rocket, you have lots of things that are measuring it from separated locations, and they all have to send that information probably to one common spot, maybe through a hierarchy of several steps, where it's then going to get processed, and the control is then going to be applied, and even that might mean that you have to send the control signal communicated up to the space probe thing to do it. You maybe can't, maybe computer in there has to couple that with some other local measurements, so that the problem is much more distributed than Kalman formulated it, despite all the great things he did. And by the same token that David just said, the information theory problem was looking at a rather narrow portion of what is a bigger problem, even if you just put it in the context of, say, this remote control problem that I just tried to talk about. Shannon was not unaware of this. And at the end of his paper on rate distortion in 1959, he said nothing about it. But in 1960, when that paper was collected into the, some kind of compendium of interesting papers of the year, that paper was put in there. And if you go to that version that's in the book, there's a few sentences that are added at the end by Shannon, I hope, because it's still under his name. But they were in some ways non-characteristic of most of Shannon's writing. And let me see if I can, he's referring to this problem. Let me see if I can say the right thing. He said, the duality that we have been investigating here between sources and channels is related to duality between information and control and past and future. And the final sentence was, we can control the future, but we have no knowledge of it. We have knowledge of the past, but we can't control it. And that's the way he ended it. So there's that's just one thing where you can try to build it in the information theory thing into a larger problem, where in this case the large thing is that information theory says that in order to send the information very reliably, that usually, although I tried to say this morning in some ways that it might not always be true, but it usually involves using longer and longer and more complicated codes and equipment in order to solve this communication problem very, very nearly optimally. And by that time, when the information arrives, it's too stale to be useful. So you need to figure out how to build these two problems together so that you do enough smart things in the information end, but not so much that it introduces latency that's sufficient to destroy the usefulness of the information. These problems, this is just an example of one big area of problem that still remains largely ununderstood. There's been some work in it, but I don't think anything you could really say is a satisfying breakthrough for how to handle that. So it's